Welcome back. Okay, last time we were talking about this. This force makes makes the object going around in circles. Okay. We're talking about this. Of course, the force is applied on the object, right? But let's say you are the one in the car. You're making a turn. You feel a force going out.
Yeah.
And which we call that. I don't know. Is that centrifugal or centrifugal? I don't know.
Same thing.
Centrifugal force, okay? But this is a fictional force. That's when you're riding in this car, right? You feel you're being pulled outside.
Yeah.
That's if you are riding in the car and the car is making a turn, right? You feel the force pulling you outside. It's called centrifugal force or centrifugal force. Okay, this pronunciation is always a problem. For instance, in chemistry, there's always this kind of thing. It's glucose is a sugar. Okay, thymine is something else. When it's glucose and something put together, they call it glucosamine. Make it hard to understand. Maybe we just do centrifugal force, whatever. Okay, but this problem is this centrifugal force is a imaginary force, but this force pulling it in is not. This is called this. This is centripetal force, but this one is probably pronounced centripetal force. But anyway, language is never supposed to be reasonable. I guess these are not the everyday words. You just do whatever you do. That's okay. Okay, that's sort of a side note. Okay. Normally, you see a couple of things I do want to point out. Normally, you see this F. This is a centripetal force. It's written as this. Okay. Real people hate this because V when you're doing a circle, you don't want to deal with V because V is not indicative on this motion, and I immediately write this into into omega, and then I didn't explain why this is superior to this. Okay. Way back when, this is the old slide, I introduced this. This is time per cycle.
Mm-hmm.
When you multiply 2 pi, this becomes radius per time. This is radius divided by time. This is how much radius did you do, radian you do per time.
Uh-huh.
You know, velocity is distance per time. Velocity equals distance, right?
Yeah.
But when you do a sort of a circular motion, right? Aren't you interested in how much angle that it went through? Radian, but this is actually angle per time.
Yeah.
So this is correspond to a speed concept.
Mm-hmm.
Because you don't really care about R, right? And you don't really care about the V then. You just care about this, how much angle it went through.
Yeah.
Yeah. So that makes this, in a circular motion, this is more obvious. If you use omega, it's better than if you use V, because V divided by. For instance, when we do, I have a problem finding all these papers. Yeah, when we do this, in this case, right? When we change the r, and not changing omega,
Mm-hmm.
and you ask, does the velocity does this force, this centrifugal force, getting greater or less?
Yeah.
If you look at this way, right, you know exactly it goes less because r goes less.
Uh-huh.
But if you look at this way, you don't know, because the velocity is changing too. R is changing, sure, but the velocity is changing too, because here you run faster or slower.
You run faster.
Really? For the same amount of time, you're going further or farther or near. Longer or shorter distance compared to this.
You what?
Okay, think about it. Okay, every 24 hours you run one cycle, right?
Yeah.
Is this longer or is this longer?
First the equator's
This is longer, right?
Yeah.
So for same amount of time, you run longer here and shorter here. Is this faster or slower?
Faster.
For a certain amount of time, one is you run longer, the one is you run shorter. Is this faster or this faster? For the
For the same amount of time, the longer one.
So is this faster or shorter? Slower.
Slower.
Slower, right? This speed becomes slower, and the r becomes shorter. Is less obvious, but this gets to the angular speed.
Yeah.
Yeah, radian per second. So this is, as long as this is not changing, r change, and it's easier to look at this. Now this is probably this particular one is probably accidental, but immediately we're gonna know the difference. But anyway, this angular velocity is also used very nicely in this kind of expression, right? It's cosine omega t. Omega is the angular velocity, 2 pi f, right? As we showed somewhere here, we showed here, right?
Yeah.
So this omega can be used pretty neatly in many places. This is neat, right? You don't have 2 pi's everywhere.
Yeah.
Okay? In down the road in physics, there are certain things that you have this 2 pi in there because there's a circle or sphere involved in it. We're not going to deal with that now. Okay, now this is, let's do it. This is angle per second, angle per time. It's, in other words, this is a velocity kind of thing, right? This is become an acceleration.
Okay.
Right? This is how, let's say this changes like a certain angle per second, right? Let's say you gradually gets faster, right? Then this thing is no longer zero. Okay? Since we call this acceleration,
Yeah.
angular acceleration, we give it, we normally call it alpha. Okay? Now, we have this, this is the velocity, right? This is A equals to dv dt, right?
Yeah.
Then we know F equals to ma, right?
Yeah.
We know this is m alpha is not F, because this is not velocity.
Yeah.
Yeah. So we introduce a a concept of two concepts actually. Okay, this is torque.
Yeah.
This is we call rotational inertia. Mass is the inertia thing anyway, right?
Mm-hmm.
The bigger the mass, the more inertia you get, harder it is to stop its motion, right? Okay, now torque is easier to understand. You have I probably should draw it here. Mess up my writing, but it doesn't matter. There's an R, right? You put a force to it, right?
Yeah.
So R is a, right? At the point O, this F caused a rotational force on the point O. Let's say this is an object here. This is an object here, right? You put an F to it, right? This creates a tendency for this thing to rotate. Yeah.
Yeah.
Now we get another thing. You remember this? The dot product of two vectors. When we do a force, this is a piece. Then we do a force like this, right?
Yeah.
And then this is a distance. This is force. This is a distance. This is a vector. This is the vector. This is call this S. It moved S, right? The same force moved same S, right? The work is S dot F, right? Or F dot S, right?
Yeah.
This equals to SF cosine theta. Yeah. This is a different kind of. Oh, this is not. We make this torque equals to R cross product F. Okay. Dot product of two vectors become a modular number. It's no longer a vector, but the cross product of the vector is still a vector.
Yeah.
The way to do it is, the way to understand it is, this is still this object, right? You have R going out to this point, right? This is the vector. Then you say you have an F, right? Right?
Yeah.
So this F obviously is different from, let's say, this F moving, same, let's say the same magnitude.
Yeah.
You can do this in any way, but you can say this F is split up into, look at this, is this F and this F. This F, it goes directly inside.
Yeah.
It does not contribute to the rotation. This F contributes to rotation,
Okay.
right? And then the actually this is not a good way to draw it. This is R. R goes this way, so this is the angle actually. This is the angle. I should draw F the other way. Let's draw F the other way. Let's draw F this way, right? Okay, let's draw it all over again. Make this a little easier. This is R, right? This F goes this way, right? Right, this is theta. This is R. This is F. This is R. Right? Right?
Yeah.
So this is F. This is the angle between R and F, because R is here, right? This force is split into the force along R and the force perpendicular to R, right? In other words, only the perpendicular force is contributing to the rotating. Following? So this F sine theta, right? This is sine theta, right? This force is
Yeah.
sine theta, right? This F sine theta, R, right?
Yeah.
But then this torque has a direction. In other words, are you rotating it this way or rotating it that way?
Yeah.
And how are you going to do that? How do you make this direction or thing? How do you define rotating this way or that way, clockwise or counterclockwise? How do you define the direction?
Like the direction sine, like if sine is negative or positive.
No. Conceptually, how do you define clockwise, counterclockwise? The problem is if you say clockwise, right? If you look at this way, it's clockwise. You look at the other way, it's counterclockwise. I'm saying, how do you define this rotation direction?
From what it is on top?
No. You give it a direction. How do you give it? How do you define it conceptually? Okay, you don't know this, right?
No.
I'll give it to you. Okay, it's called right hand rule. You know you have right hand, left hand, right? They are not. Right hand rule is this is the force, right? The force is pulling it this way, right? You use the forefinger to go that way, right? And this is the direction of the vector. In other words, this I draw it this way, right? It's moving. Let's say the force is getting it is to move this way, right?
Yeah.
The vector goes down. This is the torque. Okay. Tau. This is the all Greek letters. Yeah. You see what all alpha, whatever, all Greek letters. Yeah. In other words, if it turns this way, you use your forefinger to go along that way. That goes. Your thumb points to where it is. This is a concept of cross product. Okay.
So weird.
Now, this is how you define the direction of a rotation. Because once this thing go wild, right? At any segment, this thing, let's say just on a plane, right? You're going like this, right?
Yeah.
But here, the force to do it is torque is this way, and then this going down. This is going up. This is back down. Go back down. Of course, when you move in the 3D, and this thing can go anywhere, right? But for any small segment of this movement, the tau, because the omega d omega dt, this is the small segment, right? Then you get the alpha, and then tau goes to just that. For that moment, there is a particular direction. Yeah, it's the curve. Okay, you're gonna make a curve somehow, and you make that the plane of the curve. The tau is always perpendicular to the plane of the curve of that moment. Okay. All right. Okay. There's only one more thing, which is the this. What is rotational inertia, right? Okay, let's do that. We know this this between dv v and omega is r, right?
Yeah.
So let's do this. Okay. So to speak, right?
Okay.
This equals to r cross f, right? Equals to this is the f, right?
Yeah.
R is r. mr squared alpha. Right? I'm just substitute this in. Let's assume all There's no angle. Just everything perpendicular.
Okay.
You're putting a force. You're putting a force perpendicular, and here's r whatever. This, yeah.
Yeah.
The mass is here. When you look for that, that little bit movement, right?
Mm-hmm.
So now look at this. If you make this force, if you make this acceleration, this is your I. Remember? Here. This.
Yeah.
Right? We just said we want to have some kind of a thing here to resemble MA. Right?
Yeah.
And this thing here is mr squared. Okay? Let's say this thing is not just on one dot or some other points. Refer to this point, right?
Yeah.
So r squared dm. So every little piece of dm, right? Mass. You measure the distance to the reference point, and then r squared. You integrate this.
Mm-hmm.
That'll be your tau. Torque.
Okay.
So obviously, this thing has a different, rotational inertia reference to this point. Let's say, and the reference to this point, right? Reference to this point, r is 0. So, tau, naming the torque is 0.
Yeah.
There's no torque on it if the force is applied directly onto the object. It has to have some kind of arm, some kind of r, right, for this thing to rotate.
Yeah.
That you need a torque. Okay. All right. The different object has different torque. Let's say if it's a disc like this, right?
Yeah.
There are formulas for you to come up with this, which is kind of easy. I don't know. You have the cheat sheet for that? For the inertia, rotational inertia?
No, this is like calculus.
Okay. I thought you had a cheat sheet for everything. You'll find the cheat sheet maybe. We'll show next time. Let's see what time it is. Okay, 22. Okay. Just as we're not going to do too much of this, but anyway, just as the once this is defined, right? Just as the translational movement, how do you call that? When you move just from one place to another.
Translation.
Translational, yeah. Yeah, you have this, right?
Yeah.
This is kinetic energy, right? Now, this kinetic energy is I omega squared, obviously, right? This is easy, right?
Yeah.
For the work, this is Fs, right?
Yeah.
This is tau theta, right? Also, for momentum, okay? This is mv, right?
Yeah.
This is what?
Huh?
This is the inertia. This is the angular velocity.
That's the centra, whatever.
No, it's just the velocity. This is just the velocity. Whatever. Okay. You mean the omega, right? Omega is angle per time. For a certain amount of time, how much angle do you cross? That correspond to velocity.
Yeah.
And this inertia correspond to mass.
Yeah.
So when you write the translational momentum this way, right? The angular momentum is like this. This is if two things, when you do, for instance, there's one disk, right? Let's say one disk. Let's draw a little better. This is one disk, right? Right,
Yeah.
is rotating, and this disk on top of it, below it, is not rotating, right? Right.
Yeah.
This all of a sudden fall onto this, right? Then they rotating together. Let's call this I1. This is I2, right? This is omega 0. This is and then at the end is omega, right? So you have this I1 omega 0 equals to I1 plus I2 omega, right?
Yeah.
So at the end, this omega equals to I1 plus I2 omega 0. So when this thing fall onto this and they start to rotate together, the angular velocity moves from this one to this one. This thing, this to this. Remember that the balls example we gave? This will take a little bit of time for me to find out. Do you remember?
Yeah.
Let's see if I can find it quickly. This is now put into an order. I can't find it. I can't find it. You remember this? One ball hits another ball, and then they'll move together. This is the M, M1, M2. This is V sub 0. This is not moving. Then there's a V at the end of the thing. This is M1 V0 equals to M1 plus M2 BT. You remember that? And these two balls this is conservation of momentum. The angular momentum also conserve. So you can have the looks exactly the same way. You see that? Yeah. So that's the rotation. So what else? Okay. We'll take a break. See you later.